Have you ever wondered how a hedge trimmer works? In our MAE 3230 class, we took apart a hedge trimmer to analyze its mechanical components and fluid machines to understand how it works. First, we should explain the mechanical components of a hedge trimmer. The reciprocating blade is powered by a rotating gear inside a gearbox. The gearbox is powered by a shaft that is connected directly to a small engine. But how does the engine get its fuel? It gets its fuel with a carburetor. A carburetor mixes air and gasoline and uses a venturi, which is a pipe of varying cross-section, to accelerate the air and create a pressure difference. This pressure difference causes fuel to enter the carburetor from the gas tank and mix with the airflow. Let's explain how a carburetor works. We can explain the airflow through a carburetor using the Bernoulli equation. But before we can use the Bernoulli equation, we need to calculate the Reynolds number and determine if the flow is in viscid. A flow is considered in viscid if its Reynolds number is high enough such that the net viscous forces acting on the fluid can be neglected. For a carburetor, a Reynolds number greater than 10,000 is large enough to assume that the flow is in viscid and steady. With this steady and viscid flow assumption, we can use the steady Euler equations to derive the Bernoulli equation. But how do we find the Reynolds number of a carburetor? The equation for Reynolds number is RE equals density of the fluid times velocity of the fluid times characteristic length divided by viscosity of the fluid. We can use STP values for density and viscosity for air, and the characteristic length is the diameter of the throat at the carburetor. That leaves U, the velocity of the throat. We can determine the velocity of the airflow by finding the engine's volumetric flow rate with its parameters. For a small engine, the volumetric efficiency is around 75%. For a hedge trimmer, the engine runs on a two-stroke cycle, has a volume displacement of 25 cc, and runs at 8,000 RPM at full throttle. A two-stroke engine displaces that amount of volume in one rotation. With our calculations, we can determine that 150 liters of air and fuel enter the engine every minute. Let's determine how much air is part of the air-fuel mixture. For our engine, we'll assume that the air-fuel ratio is stoichiometric at 14.7 to 1, which represents 1 gram of fuel for every 14.7 grams of air. This ratio is by mass, so we have to convert this into volume. The density of gasoline is about 0.7429 grams per milliliter, and the density of air at STP is 1.225 times 10 to the negative third grams per milliliter. With our calculations, we can determine that the ratio by volume is 1 milliliter of fuel for every 8,915 milliliters of air. This means the 150 liters per minute that we calculated earlier is almost entirely made up of air. 150 liters per minute is equal to 2,500 cubic centimeters per second. This means every second, the engine is intaking 2,500 cubic centimeters of air when running at full throttle. We measure the diameter at the throat to be 0.699 centimeters. Converting that to area, we get 0.383 square centimeters. If we divide the volumetric flow rate of 2,500 cubic centimeters per second by the cross-sectional area, we get 65.2 meters per second at the throat of the carburetor. Now we can plug this velocity into our Reynolds number equation. We get 31,200 as our Reynolds number. Since this is greater than 10,000, we can assume that it's a steady and viscid flow in the carburetor, and now we can use the steady Euler equations to derive the Bernoulli equation. The flow is also incompressible, which means we can assume that the density is constant for an entire flow, which helps simplify the math. With our derived equation, we get a positive pressure difference of 2,430 pascals. Because this value is positive, this means that pressure 2 is lower than pressure 1. This means that there's a pressure drop at the throat, and this pressure drop causes the fuel to be injected into the carburetor. This fuel then mixes with the air and then enters the engine, ready to be combusted. As the air-fuel mixture gets combusted, the engine spins and turns the rotating motion into a translational motion. This translational motion moves the blades back and forth, cutting your hedges.